Okay, our next speaker is Felix Leditzky. He will talk about bounding quantum capacities, partial orders, and complementarity. Please.
Thanks a lot, Dong. Thanks for having me. Thanks to the organizers. Thanks also as well for accommodating the different time zones. That's very, very helpful. So this is joint work with Christoph Hirche and appeared on the archive and will also soon appear in the IEEE Transactions on Information Theory. And the goal of our work was to bound quantum capacities using partial orders and complementarity, where complementarity refers to the complementary channel. Because Ludovico talked about this, I will be short here. We talk about quantum channel capacities. So a quantum channel is a CPTP map between algebras of operators on Hilbert spaces. And we look at it as a noisy communication link. And then this quantum channel can have different capacities depending on the type of information I want to send through it. For the, in order to send quantum information or equivalently to transmit entanglement, I look at the quantum capacity of the channel. And this here is exactly the same figure that Ludovico drew, only his was much prettier. So I'll be very short again. So the idea is just that Alice shares entanglement with some inaccessible reference. She can encode her share using some encoding map into the input systems of an IID channel. So here, this is the same channel acting everywhere. That channel sends the quantum input states to Bob, who decodes them to get some system B tilde. And the hope is that this will be close to the initial entangled state with respect to some suitably chosen figure of merit. And if in the asymptotic limit I can make this perfect or faithful, then the highest achievable rate of these protocols is the quantum capacity of the channel. The other capacity we look at is the private capacity, where I now want to send classic information in a way that is secure from the eavesdropper. So here Alice has some classical random variable that she wants to encode in a quantum state ensemble. And these ensembles are collections of states defined again on n input systems to the channel. Then they're sent through the channel. And now Bob receives the states and wants to decode them to some classic information, x hat, that should be close to x. But now we want to assume that Eve actually doesn't learn anything or doesn't learn anything useful in the asymptotic limit when she also receives the environment from these channels. So the V here refers to the isometric extension of the channel, which maps the input system to the output system and some environment system E. For both of these quantum channel capacities, we have formulas. So for the quantum capacity, this is the quantum capacity theorem, which expresses the capacity in a regularized formula. And the underlying information quantity in this regularized formula is the so-called coherent information that I obtained by taking a pure bipartite state psi on A and A prime. Those are both isomorphic copies of the input system to the channel in general. And then I send the A prime system through the channel to get a bipartite state on AB. And then of that state, I take the coherent information, which is down here, the entropy of the B system minus the joint entropy. For our purposes, it's useful to look at a slightly different formulation of this in terms of difference of mutual informations. So here I take a classical quantum state. So it's a separable state where the X system in this rho XA state is classical. So it's diagonal with respect to a specified basis. And what's important here is that in this optimization of these two mutual information terms, I only look at those CQ states where the quantum part is pure. Conditioned on the classical label. And I will be consistent in a talk by always indicating such CQ states with XA. Okay, so whenever you see an X in a classical quantum state, it means it's a CQ state where the quantum states are pure. And again, here we obtain, we send the A system through the channel, through the isometric extension actually, and then we look at these two mutual informations, one for Bob and one for the environment. And optimizing this over all CQ states gives us the channel information. And then for the actual capacity, what we do is we evaluate this not just for one copy of the channel, but for a growing number of copies. And then we normalize, and then we take the largest of all of the ones that we see. Alternatively, we can take a limit n to infinity. It's the same thing. Okay, that's the quantum capacity. For the private capacity, the situation is similar. So it's again a regularized quantity where now the underlying information quantity is the so-called private information. And this is now a straightforward generalization of the query information that I wrote down before, because now we again optimize this difference of mutual informations, but we allow arbitrary quantum state ensembles. And keeping in line with this notation choice, these mixed CQ states will always be denoted by U in the classical system. Okay, so rho UA corresponds or denotes a classical quantum state with arbitrary ensembles. So the rho AU states here, the states conditioned on the classical label U, are mixed in general, whereas before they were pure. Okay, then we optimize over all those to get the channel prime information, and then we do this again for a growing number of channel copies, normalize, take the supremum or the limit, and we get the private capacity. And from writing the two information quantities like this, it's immediately obvious that the two are bounded by each other. So because the optimization, the prime information contains the optimization for the Coherent information, it's always at least as big as that. And then when you regularize, when you apply the coding theorems to this inequality, you regularize and normalize and take the limit, you then in a straightforward way get that the capacities satisfy the same inequality. But of course, you can also see the capacity inequality in an operational way, because whenever you can generate entanglement using a channel, you can always turn this into secure classical information transmission. But this is an entropic way of seeing this inequality, if you will. Okay, so we have the capacities, and as a warm-up and kind of like the main way of explaining our idea, we want to show how the capacities of a channel can be bounded by the capabilities from an information theoretic point of view of the complementary channel. Okay, so the theme of our work is that the complementary channel tells us something about the capacities of the channel. And as the motivating example, I'm actually taking other capacities, the ones that I didn't talk about. I want to be very quick here. So we actually, it's easy to see this on an entropic level for the classical capacities and information quantities. So the underlying information quantity is the Holevo quantity or chi quantity, where we just take CQ states and just look at the mutual information just for Bob, and we drop the Eve term. And regularizing this gives us the classical capacity of the channel, which is basically classical information transmission where we drop the security criterion for private capacity. And then there's also this entanglement assisted version where I also give to the sender and receiver unlimited entanglement that you can use in the NN decoding. This is just basically making this CQ state into a fully arbitrary quantum state, bipartite quantum state where we send one half to the channel and then we look at the mutual information. And it follows in a straightforward way from looking at the entropic formulas that we have these inequalities here. So the whole information, because it basically drops the mutual information with Eve, it's always at least as big as the query information. And then regularizing, apologies, this one shouldn't be here. Regularizing the same holds then for the capacities. And we can also do a similar thing for the entanglement assisted capacity, where we get a factor of 2 here, basically because of teleportation and superdense coding. And now you can show using these entropic formulas that we can actually bound these information capacity quantities again by the left-hand sides plus some error term. And this error term is exactly a information quantity or a capacity of the complementary channel. Okay. Again, I'm calling this a warm-up and not actually a result because it's really easy to just derive this using the entropic formulas. And we will spend a little more time looking at these for the quantum and private capacity, but this set of inequalities already conveys the gist of our results in a certain sense. Okay. Of course, here the last inequality here is really just by analogy, because the entanglement assisted classical capacity is a very nice capacity where we don't need any bounds because we can just compute it efficiently. Okay, but this is just to demonstrate the analogy that it also works for this capacity. Okay, so to look at the quantum and private capacity versions of these inequalities, we need to look at partial orders of quantum channels. One that already exists for quite a while in literature is that of degradability. So a pair of channels is called, satisfies the degradability order, or n is greater or equal than m in this degradability order, if and only if there's another quantum channel D called the degrading map that degrades n to m. And the D maps, of course, in a compatible way between the output of n and the input of m. This is a slight generalization actually of what's usually used in literature for degradable. So originally this has been defined in the following way, that n is called degradable if n can be degraded to its complementary channel. And dually, we call the channel anti-degradable if the complementary channel can be degraded to the channel. And so a channel is degradable if and only if its complementary channel is anti-degradable, okay? And vice versa. And we know that these partial orders imply certain statements about the capacities and information quantities. So if n is a degradable channel, then we know that the quantum and the private capacity actually coincide. So there's no separation between them. And furthermore, they're actually given by single letter formulas, namely they're all equal to this single letter channel for information. And then furthermore, in that case, you can actually also efficiently compute this. And if the channel is anti-degradable, then we know that they all, again, coincide, but they're actually always equal to 0, which you can prove using an entropic argument, but you can also prove this operationally using a version of the no-cloning argument. So we already see that these orders here imply something about the capacities. And then the work of Watanabe was to generalize these orders by working directly with the capacity quantities. And so he defined the following terminology. A channel n from A to B is called less noisy if the complementary channel has 0 private information. If you want to write this out in entropic terms, this means that if you take CQ states rho UA, then the mutual information of U and E can never be larger than the mutual information of U and B. This needs to hold for all CQ states. And degradable channels are an example of this, okay? Then you can now, instead of the information quantity, go to the capacity quantity, which means that you need to regularize. So you need to basically do this for all number of channel copies. So we say a channel is regularized less noisy if the private capacity of the complementary channel is 0. Or alternatively, in terms of entropies, you need to satisfy this inequality of mutual informations. But now this is actually on n input systems, and the n needs to be arbitrary. And then there's a third version, which is a little newer, which is called the fully quantum less noisy order. And so here we call the channel fully quantum less noisy if you basically make this CQ state relation here fully quantum. So you now say, instead of a CQ state, I take an arbitrary bipartite quantum state. I send half of it through the channel. I look at the two mutual informations between A and the environment and A and Bob. And then it needs to satisfy this entropic inequality here. This actually has also been defined in literature by Mark Wilde and collaborators. They called this the entanglement-assisted private information, where you just turn this into an entropic quantity where you now optimize over all input states. Okay, and then the fully quantum less noisy definition is that this needs to be 0. Okay, so this is a couple of orders or definitions for channels in terms of the private information and capacity quantities. And now we can all apply them to the quantum capacity quantities. And it's basically all by making things pure. Okay, so in the same way as before with coherent prime information. So we now call the channel more capable if the complementary channel has zero coherent information. And again, this means that now this mutual information inequality needs to be satisfied for all CQ states, rho XA. Remember now the convention, X means that these are CQ states where the individual states are pure, the individual quantum states. Yeah, so this is a strictly weaker condition than what we had before. We then can again regularize this. So we say a channel is regularized more capable if the quantum capacity of the complementary channel is zero, which now means that we need to do this, we need to satisfy this inequality for all number of channel copies. But again, restricting to pure state quantum ensembles. And then we can also make this fully quantum again in the same way, where instead of the CQ states, we now take pure bipartite states, but arbitrary. And then we again have to satisfy this inequality of mutual informations. And there you can also define a corresponding information quantity, which you don't want to call QE because it's not the entanglement assisted quantum capacity, but it's this quantum version of this entanglement assisted prime information that we talked about before, where you take a bipartite pure state, send half of it through the channel, and then you look at the difference of the mutual informations and optimize. Okay, and Watanabe proved about these classes of channels a remarkable set of results that generalize what we know about degradable and antidegradable channels. So Watanabe proved that if N is more capable, then that always means that the Fourier information and the prime information are always equal to each other. And yeah, okay, that's it. If the channel is regularized more capable, then the same holds for the capacity quantities. And if N is regularized less noisy, it means that they're actually all equal to each other and there cannot be any superadditivity. So here, if a channel is regularized less noisy, then the capacity quantities are equal to the information quantities, and those are single letter quantities. Okay, and so degradable channels are an example of the third class here. And antidegradable channels as well, of course. You should contrast these results with the results by Davis-Sutter et al. A couple of years later, where they kind of made some of these results approximate. And so they introduced this notion of epsilon degradable or approximately degradable, where we call a channel epsilon degradable if the complementary channel is not quite the same as, cannot quite be obtained by degrading the channel, but you can get epsilon close to it when you optimize over the degrading map. And the closeness here is measured in terms of diamond norm, which is a useful metric in quantum channels. And if we have an epsilon that satisfies this criterion, then we can write down these inequalities for the capacities that basically tell us that the superadditivity or the gap between the single letter quantity and the regularized quantity is bounded by a function, this delta 1 of epsilon and the environment dimension here. And you can do the same thing with the private capacity and also the difference between information quantities. It's going to be different functions, but what they all have in common is that when you keep the environment fixed, but you take the epsilon to 0, then they all go to 0, which then reproduces the results we know about degradability and antidegradability. And we want now, in a different way, to turn Watanabe's results and his classes of channels into an approximate form. And so if you look at the definitions from before, it's kind of obvious how to do this because you just you let the inequalities be violated, but only up to a certain parameter of epsilon, and then that's going to be that approximation parameter. So for example, we call the channel epsilon more capable if this mutual information inequality is only violated up to a certain epsilon. Okay, and alternatively, you can say that the channel information of the complementary channel can be positive, but not too big. Okay, so it's bounded by this epsilon. And then in prior work, Christoph with Daniel Stilkwanza and Cambi-Sousset proved that if we have these approximate partial orders for the quantum channels, then we can again get approximate versions of the results by Watanabe. So for example, for epsilon more capable, whose definition is written out here, this now limits the gap between the coherent information and the prime information by this parameter of epsilon. And we have similar results for epsilon regularized more capable, which bounds the separation of the two capacities. And then the other ones here, I don't want to like read them all out to you. You can look at them in paper. Problem with that is only that this epsilon, like the definition is a little unsatisfying maybe because you don't really know what that is. And so we wanted to simplify this in the work with Christoph now. And it's based on a very simple observation actually that, you can just take as the epsilon, you can just take the capacity or the information quantity of the complementary channel, okay? And then immediately these bounds turn into a rather nice form. So for example, for epsilon regularized more capable, if we just choose the epsilon to be the quantum capacity of the complementary channel, then every channel is epsilon regular more capable. Yeah. So it sounds a little vacuous, but it actually leads to very nice capacity bounds that are all phrased in terms of capacities itself. Okay, so this is our main result, or one of our main results, that we have this set of inequalities where the information quantities and the capacities of a channel are bounded in terms of these corresponding quantities for the complementary channel. And you can actually also prove them somewhat directly without going through this approximate partial order business by just using the entropic formulas in a clever way. And let's take maybe a closer look at these bounds. So the first two bounds here tell us something about how much quantum and private capacity can be separated, right? Because we saw before that the left inequalities are always true, either based on entropic or operational arguments. And then the right-hand sides bound the capacity in terms of the left-hand side plus some error term. And the error term is just given by a quantity of the complementary channel, okay? And so, for example, here we have this very nice inequality that the private capacity is upper bounded by the quantum capacity of the channel and that of the complementary channel, which I find very pleasing in some way. And the other two inequalities you can understand as inequalities that bound the amount of superadditivity you can get. Okay, so we have channels for which there's a strict gap between the channel information and the capacity quantity. And then our bound tells us that that gap is controlled or bounded by this entanglement assisted prime information. For the prime information, it's a little more complicated about. And for example, one thing that this bound gives us is a new insight that if I have a channel that has zero capacity for both the channel and its complementary channel, then this bound implies that the private capacity also has to be zero. I will come back to that later, okay? Another cool thing is that this actually gives us numerical bounds on private capacity from numerical bounds on quantum capacity. So this is somewhat like an annoying problem that for the private capacity, there's not too many useful bounds that you can actually compute. Whereas for the quantum capacity, by now, there's a large body of work that has some that you can, like, for example, using semi-infinite programming. And so now this gives you an easy way of doing this for the prime capacity of a channel, okay? It's sometimes not very useful, but sometimes it is useful, and I'll also come back to that later. Okay, another thing that we do in the paper is that we actually apply this all to the static case of states. So here, instead of a channel, we now have just a bipartite state shared between Alice and Bob, or rather, IID copies of it. And then we can again look at what's the largest quantum key or key that they can distill from copies of this bipartite state. And if we only allow one-way classical communication from Alice to Bob, then this is the exact state analog of the private capacity of a channel. Okay, and so we call this the one-way distillable key. And if we want to distill entanglement from the bipartite state instead of secure key, then the corresponding quantity under one-way LLCC operations is the one-way distillable entanglement. And those are denoted by K with the forward arrow and D. For operational reasons, we again have this inequality here. And there's also underlying information quantities, and then those are regularized versions of these information quantities. But I didn't want to show too many entropy quantities. Okay. And in terms to show, in order to show our results here, we adopt the somewhat non-standard notation that we call the complementary state rho ABC, just to have the analogy with the complementary channel. But it really is just taking a purification of your mixed state and then tracing out Bob to get a state on Alice and Eve. So this is just rho AE, but we choose this more suggestive notation, maybe. Okay. And then we can again define these partial orders or approximate partial orders by limiting the one-way distillable key or entanglement of the complementary state. Okay, and so we call them epsilon more secret if we have this inequality, and epsilon more informative if we have the equality for the one-way distillable entanglement. And then we prove in the paper that we have the exact, like we have an analog of our capacity bounds now in terms of these distillable entanglement and distillable key quantities. And they have the same form, basically. So again, for example, here, this third one is the exact, sorry, the fourth one, the third and the fourth one are the exact analog of the bounds I showed before for quantum and private capacity. And so these operational bounds are, again, they have the same benefits as before. Okay, so they give you new insights that the key of a bipartite state is 0 if you cannot entangle either to Bob or to Eve. And it also gives you a way of numerically estimating them with just using bounds on the distillable entanglement. And the situation here is similar to the channels. So we have more bounds for the distillable entanglement than for the key, I think. Okay, if I have a little bit of time left, I want to go through some open problems. So one thing that is basically open since the work of Watanabe is to ask whether the class of degradable channels and regularized less noisy channels is actually separated. Okay, so as a reminder, a regularized less noisy channel has a complementary channel with 0 private capacity. And a degradable channel is one where the complementary channel is obtained by degrading the actual channel. And from this, it follows that the complementary channel has 0 private capacity. So degradable channels are always regularized less noisy, but it's not known whether there is a regularized less noisy channel that's not degradable. Okay. And what we found in our paper is a curious connection to the superactivation of private capacity. So as a reminder, superactivation means that you take 2 channels that each have 0 capacity, in this case, private capacity. But when you use them together or jointly, that thing now has strictly positive private capacity. Okay? And we don't have an example of superactivation of private capacity yet. But if there is one, then that actually implies that the 2 classes of channels are strictly separated. So this, at least in our opinion, kind of is one more motivation to look for superactivation of private capacity. And so the question is, why don't we have that example? Because we now understand the superactivation of quantum capacity fairly well, I would say. And the problem is that for superactivation, you either, in a way that we understand it, at least, you either need 2 different classes of 0 capacity channels, or you need one class that is not closed under tensor products. Okay. And the only class of channels with 0 private capacity that we know is that of antidegradable channels, which is closed under tensor products. Okay. So if you take 2 antidegradable channels, then the tensor product will again be antidegradable. So that thing can't have positive capacity, private capacity. And so then based on our bounds, we now had an idea. Okay, what if we take a channel that is PPT to both Bob and Eve? So both the channel and its complementary channel are PPT, which means that they have 0 quantum capacity. because then by our bound, this would imply that they have zero capacity, also for private information transmission. And so let's call these channels by PPT channel. We weren't really sure whether there was terminology there. And we thought, okay, maybe there's an interesting example of something that has actually, that is interesting and satisfies this condition. Bad news was that shortly after we put this out, there was a proof that these channels are actually not very interesting because they're always entanglement breaking. So this is a very nice paper by Alexander Müller-Hermes and Satwik Singh, a couple of weeks after we posed this question, who proved that every bi-PPT channel is entanglement breaking. And of course, entanglement breaking channels you can never use in a superactivation result because they will just break every entanglement. However, I am still interested in this setup because what we did in numerical studies is that we found approximately bi-PPT channels. Okay, so those are channels that are almost PPT to both Bob and Eve. But they are actually non-trivial in a sense that they have strictly positive channel information and therefore strictly positive capacity. Okay, so they cannot be entanglement breaking. And then actually also applying our bound for these channels then also shows that our capacity bound can in certain situations be useful as a numerical tool as well. Okay, because the bound that we get from our capacity bound is actually better than the private capacity bound that you can evaluate that's in the literature. So I'm very interested in these examples, and maybe we can find maybe that those can help towards a superactivation of private capacity. That would be very cool, I think. And with that, I would like to conclude. So we found or we derived these operationally meaningful bounds on quantum and private capacities of both channels and states in terms of the complementary object, the complementary channel or the complementary state. And the proofs rely on these approximate partial orders. You can find the paper in the archive and soon in the transactions. And with that, I would like to conclude, and thanks for your attention.
Okay, thanks, Felix, for the interesting talk. We have time for a quick question.
I have a question.
Okay, please.
This is Mark. Thanks, Felix, for your talk. It's very interesting. I might have asked you this already. Is there any hope to apply this kind of reasoning to the two-way assisted capacities?
Yes, you have asked this before, and the answer is still I don't know. This is much harder.
One might hope for
to prove
as an analogy to your. I think a very interesting band, like you said, is the private capacity is bounded from above by the sum of the quantum capacity of the original channel and the complement. And one might hope to get that kind of thing for the two ways.
Yes. This would also, I mean, it wouldn't surprise me if someone has also thought about this in the state case,
right?
With distillable key and distillable entanglement. Yeah, I agree. It's a good question, and I would let me conjecture that similar bounds should be true also for two-way.
Oh.
It would be strange if they weren't, I think.
Okay, seems worthwhile to think about.
Okay, let's thank Felix again. Thank you.
Thanks a lot.
Debbie Leong raised her hand to ask a question.
Yes, thanks for that opportunity.
Okay.
Hey, David.
Well, I have some concern about the situation with two-way assistance, because the notion of degradability will not play as much of a central role anymore, right?
Yes.
And so I just don't see how, I mean, it's not just the fact that we have no capacity formula, but the whole, the heart of all these results seem to not really hold in that setting.
I agree that the orders would have to be adapted to this, for sure.
Is there even a notion of degradability in the two-way assisted setting?
A notion that similarly implies additivity, you mean? Or like...
Yes.
Don't. think so.
The main tool is this teleportation simulation trick where everything simplifies. But I don't know. Yeah, it's true. I mean, the complement. Yeah.
Well, let's talk more at the break.
No, it's a very good point, Debbie, that obviously the way this is built up makes use of these relations between channels that only have relevance in the one-way setting, in a sense. And so for a two-way, you would have to go through the corresponding one. I mean, somehow the role of antigradability is a little bit played by, no, you can't say that, but I mean, PPT is relevant in the two-way case, right? But PPT is not an order. It's defined, or it's not defined in terms of the complementary channel. Let's put it that way.
Right.
It's an intrinsic property, so to say. I don't know, maybe there's a link to quantum broadcast channels as well, a little bit. But maybe Mark knows more about this. I don't know.
I don't. We can continue in the breakout room.
Yeah, for sure. Thanks for the questions.
Thanks.
So any question? No. Okay, if no, let's thank Felix again.